Hello, I'm Katie Smith from the Centre for Ecology and Hydrology, and I'm going to be talking to you about some flow data that we've produced, which is reconstructions of daily river flow for 303 catchments in the UK, and it runs from 1891 through to 2015. This has been collaborative work with several members of my team, including Maliko, Jamie Hanford and Christelle Prudhomme, and it's also been collaborating with the Met Office and several other partners of the UK Drought and Water Scarcity Programme. So some of the motivation for this work is that the UK has a limited number of streamflow records prior to 1961. As you can see in this graph, we've had a massive increase in streamflow records, streamflow stations about in the 1960s, but before then we have a very limited number of records and they're very scarce around the country. So it's quite hard to build a systematic picture of river flows across the whole of the UK before the 1960s. So what this research has been looking at is using hydrological models to reconstruct historic streamflow, and we've also been hoping that this will benefit in UK hydrological forecasting. This work has been part of two of the UK Droughts and Water Scarcity Programme projects. The historic part of it is the Historic Droughts project, and the forecasting part of it is from the Impetus project. So to do hydrological modelling, which is what we've been doing for this, you need two inputs for a lumped catchment model. So these models are run on a daily basis, and they need firstly precipitation, so rainfall that goes into the model, and also the potential evapotranspiration, so how much of the rainfall is evaporated back off the land surface. So in order to run these models on a daily basis, we need daily inputs of precipitation and potential evapotranspiration. So as part of the Historic Droughts project, we've had some other researchers have been working on developing these data sets for us, and they are freely available or will be freely available very soon, and I'll talk to you about that a bit more in a moment. But firstly, the precipitation. So we've been working in collaboration with the Met Office, and they've conducted a very large climate data rescue and recovery programme, which digitises the data from various sources, including maps and charts and graphs, and lots of handwritten archive records. And as part of this project, what they've managed to do is they've managed to create daily rainfall and temperature data all the way back to 1891. They've also managed to produce monthly rainfall data all the way back to 1862, as well as monthly minimum and maximum temperatures from 1891. And this, as you can see in some of these plots, has greatly increased the spatial coverage and the detail of the rainfall data that we've got across the UK. So this has been really useful, and this daily data is what we've been using in our catchment modelling. And then the second data set that we need is potential evapotranspiration. Later than 1961, we used the Pemberton-Monteith equation, which requires quite a lot of climate variables to produce. However, before 1961, we don't have all of those records. We don't have all the details of all the variables we need. So Maliko Tanguy has been looking at using the Met Office's temperature data that I've just mentioned, that they've recently digitised and recovered. So that's daily temperature data, and she's used that to derive some potential evapotranspiration using temperature-based McGuinness-Born equation. So this data set is on a daily time step. It's a 5-kilometre gridded data set, and it runs from 1891 to 2015. This is freely available now on the Environmental Information Data Centre. So if you go and have a look, if you have a Google for the PET data set, it's a daily record all the way through for those nearly 125 years worth of data. And the method that Maliko used to derive this, as well as a lot of testing of all the different methods that you could use in the calibration of the temperature-based equation, and in trying all sorts of different temperature-based equations, has been published now in Earth System Science Data last year. So what we did then is we identified 303 catchments across the UK that are the basis of this reconstruction. These are catchments that have enough observed data for us to test the skill of the model to show that the model's doing well. But also these are catchments that are particularly of interest, or some of them are near natural catchments, so they're more likely to do well in the modelling that we've produced. And the hydrological model that we've used is the AirGR suite of packages. It's an R package. It's freely available from CRAN, so you can look it up. And we've used GR4J, which is their daily 4-parameter model. It's quite a simple catchment model. It's very effective. It runs very well in the UK, and it has 4 parameters. Very simple. There's the production store capacity. There's an inter-catchment exchange coefficient, which is a bit like a loss function. There's a routing store capacity, and then there's a unit hydrograph time delay. So what we had to do in order to get these reconstructions was to calibrate this model and get these 4 parameter values as good as we could. However, we also wanted to account for the uncertainty in these parameters. So there might be different combinations of parameters that lead to a similar flow out of the end of the model from the rainfall and the PET values. So we ran 500,000 different sets of parameter values, and then so we ran this on the Jasmine supercomputer. Took a couple of weeks for us to run it, but this has given us a really good understanding of the parameter uncertainty in the model. The way we've calibrated it then has also been using a multi-objective optimization approach. So the model is calibrated using more than one equation. So usually a model will be calibrated with something like the Nash-Sutcliffe efficiency equation. But this is quite biased towards high flows. We wanted to make sure we covered high, medium and low flows to get a good understanding of the whole flow regime. So we used 6 different metrics: Nash-Sutcliffe, the log Nash-Sutcliffe, the mean absolute percent error, which gets a good understanding of the whole range of flows, the percent bias, which gets a good understanding of the bias of the model overall, the total water balance, and then 2 low flow metrics: the error in Q95, which is a flow exceeded 95% of the time, and the error in the mean annual minimum on a 30-day accumulation period. So we then applied a ranking algorithm. So we had 500,000 different model runs, and we had these 6 metrics for each of them. And we ran a ranking algorithm that determined which were the best and which were the worst, and ranked them from 1 to 500,000. And we extracted the top 500 runs to give a good understanding of the uncertainty involved in the models. We also extracted the best one run. So if users are looking for one flow time series that they can run, if they're restricted in what they can run in terms of their ongoing environmental impact models, then there is a one best run. But it's important to note that the model performance varies quite significantly by catchment. There are some catchments that the model does really, really well. These 6 metrics are all pretty outstanding, and there are other catchments that may have factors such as human influence. There might be heavy abstraction or snow melt that the model might not be taking into account. So we've produced some maps and to have a look at these values. And yeah, as I've said, the model varies in its performance for each of the catchments. For example, there are a few odd catchments down in the south and east where there's quite a lot of significant abstraction going on, where the model doesn't quite do so well in some of these metrics. And then there's also some areas up in Scotland which we think are due to snowmelt, where the model doesn't quite do so well. This work is, these sorts of things are being explored by Gemma Coxon, and she's produced a video that explains the differences in both this model, the grid-to-grid model, and the dynamic top model, and we're looking at how the different models cope with these sorts of problems. And it's interesting to see that in a lot of them, we have similar problems across all of the different models in certain regions of the country. So yeah, it's important to check that if you're looking at a certain catchment. So this flow data that covers nearly 125 years worth of data is freely available from the Environmental Information Data Centre. You need to sign up to be able to get into it, and I'll show you the website in a second. There's a big supporting documentation file which explains in a lot more detail what I've just gone over, how we got to this data and how we calibrated the models and how we've extracted it all. And so and I'll show you on here as well how you get hold of the data. There's 2 data sets effectively. There's the one best run for each catchment, and then there's a series of 500, the best 500 as well. So if you want to have a look at them with the parameter uncertainty, then you can have a look at the 500 runs as well. There's also what we call a Shiny app. So Shiny apps are named so because they're developed using the Shiny package in R. And they're just basically websites, interactive websites that you can have a look at. So we've produced one that looks at all of the model performance in each of the catchments, and also you can have a look at the flow data and zoom in on the flow data to have a look at how it compares against the observed, and I'll show you that in a second. I'd finally like to mention that Lucy Barker and a few other members of the team have derived some standardized Streamflow Index data, and this is based on this flow data. She has calculated the standardized Streamflow Index, which is basically a way of allowing a comparison in the model, a comparison of the data over space and time, and looking at how the data moves away from the average. So if there's a period of significantly dry, lower flows, or if there's periods of significantly higher flows, it shows you that variation in the stream flow from its climatological average. So it's quite easy from there to pick out drought events that we've been particularly interested in. So yeah, this data as well is available on the Environmental Information Data Centre, freely available to download for all 303 catchments for the same time period. So for now, I'm going to run across to the internet and show you a demonstration of the Shiny app and how to get hold of the data. Okay, so this is the website where you can get hold of the Streamflow data. So this is on the Environmental Information Data Centre. There's a front page here that tells you its DOI and tells you a bit of information about what there is in the data. And then there's a handy little link here to download the data and to download the supporting documentation. So as I said, you need to have a login to be able to get hold of this data, but it's all free. You just need to log in. So if you go to download the data, then there's two folders that you want to have a look at. There's one called Single Run, and this is where the top best run is stored. So you've got them for these are the catchment IDs. These are NRFA, the National River Flow Archive ID numbers for each of the catchments that we've calibrated the model for and run the flow data for. So you can cross-check those catchments against the National River Flow Archive as to where they are. And then similarly again on the ensemble data, there's data sets of the 500 top runs as well, and each of those has a metadata file to show you the model performance and a few other statistics for each of the runs. So that's how you get hold of the flow data. There is also as I said, the Shiny app. So this is what the Shiny app looks like. You come onto this front page here. It tells you a little bit about the project. There's a map down the left-hand side where you can click on the different evaluation metrics, the calibration metrics that we've used. As I mentioned earlier, there's Nash Sutcliffe efficiency, log Nash Sutcliffe efficiency, the mean absolute percent error, absolute percent bias, and then the error in the mean annual minimum on a 30-day accumulation period and in Q95. So you can choose your evaluation metric and you can then zoom in on the map, find the catchment of interest, and have a look at all those statistics as well. So you can see here that some of the catchments, particularly in the south, have a very good Nash Sutcliffe score. Some in Scotland where there's snowmelt influences, the scores are a bit lower. Similarly, there's a scatter plot here which shows you the scores of different evaluation metrics, and as you select a different evaluation metric here, it will update the map and the chart to the evaluation metrics that you've chosen. So this shows you the scores over the calibration period of 1982 to 2014, and then against the observational record, which varies in length according to the catchment. So, I mean, they're pretty good on a one-to-one line, so it shows you that the model's doing well, even in the records that are before the calibration period, so it's fairly well calibrated. Similarly, there's some more plots here as well that there's plenty of information in here for you to look at, but yeah, they just show you the score against various thresholds that we've set, and also the range of a bit about the range of uncertainty in the model. So that's a lot of information on the performance of the model. So if you're trying to choose a good catchment, then pay close attention to that. But also there's this second page here, which is the flow data. Again, you can choose different catchments here. Please be patient. It takes a long time to load this graph as it's processing 125 years worth of daily flow data. So it might take a minute or two to load. I've preloaded this one up for you to look at. This is one of our pretty good catchments. You can see the observed flow here in orange, and the modelled flow is in turquoisey colour. And this nice interactive format means you can click and zoom in on the flow at a particular period. I've also included the top 500 in that shaded turquoisey colour there, so you can see what that looks like, and then you can scroll along as well. So if we find a drought event, the 1975-76 drought event there, you can see the observations fall a little bit lower than the models, but the model's doing pretty well there. Finally, there's another tab just about the data. This is a bit of a summary of the supplementary information that you can download from the EIDC website as well. So this is just another recap of how we've calibrated the model and how we've got the data. I also mentioned the standardized Streamflow Index data. That's also on the EIDC. Lucy Barker will be talking to you more about this. So yeah, you can download that on the EIDC as well. There's plenty of information. And Lucy has also created a Shiny app that shows you more about the drought events that she's extracted from the flow data. So this shows you the standardized Streamflow Index, let's say over a 12-month accumulation period for this catchment. And there's a massive amount of information on this website for you to play with, and Lucy will tell you more about it. So I hope that's been a helpful introduction to our flow data. Please, by all means, email me if you have any questions. But the data is all freely available, and the Shiny app should help you peruse it and explore it till your heart's content. Thank you.